Every second, approximately 100 billion photons from the Sun strike each square centimeter of Earth's surface, having completed a journey of 93 million miles in exactly 8 minutes and 20 seconds. Yet from the perspective of those photons themselves, something extraordinary occurs that challenges our most fundamental understanding of time, space, and experience itself. According to Einstein's special relativity, time dilation approaches infinity as velocity approaches the speed of light, meaning that for a photon traveling at light speed, time effectively stops. This creates one of the most profound paradoxes in modern physics. If time stops for objects moving at light speed, how can light traverse the vast distances of space? How does a photon experience its journey from the surface of a distant star to your retina? And what does this tell us about the fundamental nature of spacetime, causality, and reality itself? The implications reach far beyond academic physics. Understanding the photon's relationship to time and distance reveals deep truths about the structure of reality, the nature of information transfer across cosmic scales, and the limits of physical law. When we grasp how light experiences or fails to experience its journey through space, we uncover principles that govern everything from quantum mechanics to cosmology. Consider a photon emitted from the Andromeda Galaxy, our nearest galactic neighbor located to 0.5 million light-years from Earth. From our perspective, this photon travels for 2.5 million years, crossing an incomprehensible expanse of space before finally reaching an astronomer's telescope. Yet according to relativistic physics, from the photon's reference frame, its departure from Andromeda and its arrival at Earth occur at precisely the same instant. No time passes. No distance is traversed. This paradox exposes the deepest mysteries of spacetime geometry and forces us to question what we mean by experience, journey, and distance at the most fundamental levels of reality. Dr. Brian Greene of Columbia University describes this phenomenon as revealing that space and time are not the fixed absolute entities our intuition suggests, but rather malleable aspects of a unified spacetime fabric that depends entirely on the observer. As frame of reference, the mathematical framework of special relativity, developed by Einstein in 1905, provides precise equations describing how time dilation and length contraction affect objects moving at relativistic speeds. As velocity approaches the speed of light, time slows toward zero and lengths contract toward zero from the perspective of the moving object. For a photon moving at exactly light speed, these effects reach their mathematical limits, time stops completely, and distances vanish entirely. Yet photons clearly do traverse space and carry information across cosmic distances. Light from distant galaxies reaches our telescopes after traveling for billions of years. Laser beams propagate across laboratories, and fiber optic cables transmit data around the globe. How can we reconcile the mathematical prediction that photons experience zero time and zero distance with the obvious fact that electromagnetic radiation propagates through space and enables the transmission of information and energy? The resolution of this paradox requires understanding that photons exist in a fundamentally different relationship to spacetime than massive objects. While we can mathematically describe what happens as objects approach light speed, photons themselves cannot be said to have a reference frame in the conventional sense. They exist at the boundary of spacetime geometry, where our usual concepts of time, distance, and causal sequence break down. Professor Sean Carroll of Caltech explains that photons live on the light cone, the mathematical boundary in spacetime that separates events that can be causally connected from those that cannot. This boundary position gives light its unique properties. It can connect any two points in spacetime regardless of their spatial separation. Yet it experiences no passage of time or traversal of distance in doing so. This fundamental property of light has profound implications for information transfer, causality, and the structure of physical law. The fact that electromagnetic radiation can instantly connect distant regions of spacetime from its own perspective enables the universe to maintain causal coherence across cosmic scales. Without this property, the synchronized behavior we observe in cosmic phenomena would be impossible. Tonight, we're investigating one of the deepest mysteries in modern physics, the paradoxical nature of light's relationship to time and distance. We'll explore how special relativity predicts that time stops at light speed, examine what this means for the photon's experience of its journey, and discover how this paradox reveals fundamental truths about the nature of spacetime, causality, and information transfer. We'll uncover how length contraction and time dilation work together to create the photon's unique perspective. Investigate what modern physics tells us about the nature of electromagnetic radiation, and examine how quantum field theory provides additional insights into light's relationship to spacetime geometry. We'll explore the implications for causality, information theory, and our understanding of cosmic communication across vast distances. If you're fascinated by the deepest mysteries of space-time and the nature of reality itself, subscribe and hit the thumbs up button. And hear us a question that might fundamentally change how you think about light and distance. If every photon that has ever reached your eyes experienced zero time during its journey, what does this tell us about the nature of vision, information, and your connection to the cosmos? Share your thoughts in the comments. I'll pin the most insightful response. The journey we're about to undertake will challenge your intuitive understanding of time, space, and motion while revealing the elegant mathematical structure that governs the most fundamental aspects of reality. From Einstein's revolutionary insights about spacetime to cutting-edge research in quantum field theory and cosmology, we're exploring questions that probe the very foundations of physical existence. We'll discover that light's paradoxical relationship to time and distance isn't just a curious mathematical artifact, but a fundamental feature of reality that enables information transfer, maintains causal coherence, and makes possible the very existence of structured matter and energy in our universe. The answer to how light experiences distance reveals deep truths about the nature of existence itself. Now let us begin our exploration of one of the most profound paradoxes in modern physics, and discover what it tells us about the fundamental nature of reality. Einstein's revelation, the foundation for understanding light's paradoxical relationship to time and distance, lies in Albert Einstein's revolutionary 1905 paper on the electrodynamics of moving bodies, which introduced special relativity and forever changed our understanding of space-time and motion. Einstein's breakthrough emerged from his attempt to resolve inconsistencies between Newtonian mechanics and Maxwell's equations for electromagnetic radiation, leading to insights that revealed the fundamental structure of spacetime itself. The central postulate of special relativity states that the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. This seemingly simple statement has profound consequences that challenge our intuitive understanding of time and space. And like other velocities, which appear different depending on the observer's reference frame, light speed remains absolutely constant at approximately 299,792, 458 meters per second for every possible observer. This constancy of light speed forces us to abandon the classical notion that time and space are absolute, fixed quantities that flow uniformly for all observers. Instead, Einstein showed that time and space are relative quantities that depend on the observer's state of motion. As objects move faster relative to an observer, time slows down and lengths contract in the direction of motion, effects that become increasingly dramatic as velocities approach the speed of light. The mathematical expressions for time dilation and length contraction involve what physicists call the Lorentz factor, represented by the Greek letter gamma. This factor equals 1 divided by the square root of 1 minus the velocity squared divided by light speed squared. As velocity approaches light speed, the denominator approaches zero, causing the Lorentz factor to approach infinity. This mathematical behavior reveals the extreme nature of relativistic effects at light speed. For time dilation, the Lorentz factor determines how much time slows down for a moving object relative to a stationary observer. At everyday speeds, this factor remains virtually equal to 1, meaning time dilation effects are negligible. However, as velocity increases toward light speed, time dilation becomes increasingly significant. At 90% of light speed, time runs about 44% slower. At 99% of light speed, time runs about 14% as fast as normal. At 99.9% of light speed, time crawls at just 4.5% of its normal rate. The mathematical limit of this process reveals something extraordinary about light speed itself. As velocity approaches exactly the speed of light, the Lorentz factor approaches infinity, meaning time dilation becomes infinite. For an object moving at exactly light speed, time stops completely relative to all other reference frames. This mathematical prediction leads directly to our central paradox: if time stops for objects moving at light speed, how can light traverse distances that require time to cross? Length contraction follows a similar mathematical pattern. Objects contract in their direction of motion by a factor equal to 1 divided by the Lorentz factor. At light speed, this contraction becomes infinite, meaning distances shrink to zero from the perspective of the moving object. A photon traveling from Alpha Centauri to Earth would experience the 4.37 light-year distance as literally zero, no distance to traverse whatsoever. Professor Lisa Randall of Harvard University emphasizes that these effects aren't illusions or measurement artifacts but represent fundamental features of spacetime geometry. Time dilation and length contraction reflect the underlying structure of four-dimensional spacetime, where space and time form a unified fabric that responds to motion in mathematically precise ways. Einstein's equations describe objective physical relationships that govern all motion and energy in the universe. The experimental verification of special relativity has been extensive and precise. Particle accelerators routinely accelerate electrons, protons, and other particles to velocities exceeding 99.9% of light speed. And these particles exhibit exactly the time dilation and energy relationships predicted by Einstein's equations. GPS satellites must account for time dilation effects due to their orbital velocity and gravitational environment to maintain accuracy within meters. One of the most dramatic confirmations comes from cosmic ray muons and stable particles created when high-energy cosmic rays collide with Earth's atmosphere. These muons have extremely short lifetimes of about 2.2 microseconds before decaying. At their typical speeds of 98% light speed, time dilation extends their lifetimes by a factor of about 5, allowing them to reach Earth's surface despite being created at altitudes where they would normally decay long before arrival. The universality of light speed creates what physicists call the light cone structure of spacetime. Every event in spacetime lies at the center of a light cone, a geometric boundary that separates the regions of spacetime that can be causally connected to that event from those that cannot. Events inside the light cone can influence or be influenced by the central event, while events outside the light cone cannot have any causal relationship with it. This light cone structure reveals why light speed represents a fundamental limit in nature. Information cannot travel faster than light because doing so would violate causality by allowing effects to precede their causes. The constancy of light speed ensures that causal relationships remain consistent across all reference frames, maintaining the logical structure of cause and effect that makes physical law possible. Einstein himself was deeply troubled by some implications of his theory, particularly the way it seemed to eliminate absolute simultaneity. Events that are simultaneous for one observer may occur at different times for observers moving relative to the first. This relativity of simultaneity means there is no universal now, no absolute present moment that applies throughout the universe. The deeper implications of special relativity extend to our understanding of mass, energy, and the structure of matter itself. Einstein's famous equation E equals mc emerges directly from special relativity and reveals that mass and energy are interchangeable quantities. As objects approach light speed, their relativistic mass increases without limit, requiring infinite energy to actually reach light speed. This provides another reason why massive objects cannot travel at light speed, only massless. Particles like photons can travel at light speed. And they must always travel at exactly this speed. They cannot be slowed down or sped up. This constraint means that photons exist perpetually at the boundary of spacetime geometry, experiencing infinite time dilation and infinite length contraction that reduces their subjective experience of time and distance to zero. Dr. Kip Thorne of Caltech notes that special relativity reveals light as existing in a fundamentally different relationship to spacetime than massive matter. while massive objects move through spacetime along paths called world lines that have finite slopes in spacetime diagrams. Photons follow null geodesic paths with infinite slopes that represent motion at exactly light speed through spacetime. These null geodesics have the remarkable property that their spacetime interval, the relativistic measure of separation between events, equals zero. This mathematical fact means that from the photon's perspective, its emission and absorption events are separated by zero spacetime distance, occurring at the same location in spacetime despite being separated by vast spatial distances and time intervals from other reference frames. The mathematical structure of special relativity thus predicts that photons experience no passage of time and no traversal of distance, regardless of the spatial separation and time intervals observed by other reference frames. This prediction leads directly to the central paradox we must resolve: how light can carry information across cosmic distances while experiencing neither time nor space. Einstein's revelation about the nature of spacetime provides the foundation for understanding this paradox, but the complete resolution requires deeper investigation into the nature of photons, the geometry of spacetime, and the fundamental principles that govern electromagnetic radiation in our universe. Time dilation. To understand how time stops at light speed, we must examine the precise mathematical and physical mechanisms of time dilation. One of the most counterintuitive yet experimentally verified predictions of special relativity. Time dilation reveals that time is not the universal constant our intuition suggests, but rather a variable quantity that depends fundamentally on motion through space and the observer as reference frame. The mathematical description of time dilation begins with the Lorentz transformation, which relates the coordinates of events as measured by different observers moving at constant velocities relative to each other. For an object moving at velocity v relative to a stationary observer, time passes more slowly for the moving object by a factor of gamma, where gamma equals 1 divided by the square root of 1 minus v squared per c squared. As velocity increases, this gamma factor grows larger, meaning time dilation becomes more pronounced. At 50% of light speed, gamma equals 1.15, so time runs about 15% slower. At 90% of light speed, gamma equals to 0.29, meaning time runs less than half as fast. At 99% of light speed, gamma equals 7.09, so time crawls at just 14% of its normal rate. At 99.9% of light speed, gamma reaches 20 to 0.4, with time moving at merely 4.5% of normal speed. The mathematical limit of this process occurs exactly at light speed, where the denominator of the gamma factor becomes zero, causing gamma to approach infinity. This infinite time dilation means that for an object moving at exactly light speed, time stops completely relative to all other reference frames. No time passes whatsoever during the object's journey, regardless of the distance traveled or the time intervals observed by stationary observers. Dr. Brian Cox of Manchester University explains that time dilation isn't a perceptual effect or measurement artifact but represents a fundamental feature of spacetime geometry. Clocks moving at high velocities actually run slower, particles with short lifetimes actually live longer, and all physical processes actually occur more slowly from the perspective of stationary observers. The slowing of time is as real and objective as any other physical phenomenon. Time dilation. The physical mechanism underlying time dilation emerges from the fundamental structure of spacetime as a four-dimensional continuum where space and time are intimately connected. Motion through space necessarily involves motion through time, and the total speed through four-dimensional spacetime remains constant for all objects at the speed of light. Objects at rest move through time at maximum rate but don't move through space. Objects moving through space must divert some of their motion through time into motion through space. This explains why time slows down for moving objects. They are using up some of their motion through time to move through space instead. The faster an object moves through space, the slower it moves through time, maintaining a constant total velocity through four-dimensional spacetime. At light speed, all motion occurs through space, leaving none for motion through time, which stops completely. Experimental verification of time dilation has been extensive and precise across multiple domains of physics. The most famous confirmation involves atomic clocks flown on high-speed aircraft and compared with identical clocks remaining on the ground. These experiments, first performed by Haffel and Keating in 1971, measured time differences of precisely the amounts predicted by special relativity, confirming Einstein's predictions to within experimental error. Particle physics provides even more dramatic confirmations through the behavior of unstable particles at high velocities. Muons created in cosmic ray collisions high in Earth's atmosphere have lifetimes of only 2.2 microseconds in their rest frame. At their typical speeds of 98% of light speed, they should decay long before reaching Earth's surface. Yet many muons are detected at sea level because time dilation extends their lifetimes by the predicted factor of about 5. The Global Positioning System provides a practical demonstration of time dilation effects that impact daily life. GPS satellites orbit Earth at velocities of about 14,000 kilometers per hour, causing their onboard atomic clocks to run slower than identical clocks on Earth's surface by about 7 microseconds per day, due to special relativistic time dilation. Without correcting for this effect, GPS positioning would accumulate errors of several kilometers per day. Modern particle accelerators routinely accelerate electrons, protons, and heavier particles to velocities exceeding 99.9% of light speed. And these particles exhibit precisely the time dilation effects predicted by special relativity. At the Large Hadron Collider, protons accelerated to 99.9999% of light speed experience time dilation factors exceeding 700, meaning that processes occurring in 1 second of laboratory time correspond to less than 0.001 seconds in the proton's reference frame. The mathematical precision of time dilation extends to the quantum mechanical level, where individual particles exhibit temporal behaviors that precisely match relativistic predictions. Quantum field theory incorporates special relativity as a fundamental requirement, ensuring that all quantum processes respect the time dilation relationships predicted by Einstein's equations. Time dilation also affects electromagnetic radiation itself, though in subtle ways that require careful analysis. When light travels between reference frames moving at different velocities, its frequency shifts according to the relativistic Doppler effect, which depends on time dilation between the source and observer frames. This frequency shifting provides another experimental confirmation of time dilation effects. The philosophical implications of time dilation challenge our fundamental concepts of temporal flow and simultaneity. The discovery that time rates vary with motion eliminates the possibility of absolute simultaneity. There is no universal now that applies throughout the universe. Events that occur simultaneously in one reference frame may be separated in time when observed from frames moving at different velocities. Professor Carlo Rovelli of Aix-Marseille University argues that time dilation reveals time itself to be an emergent property of thermodynamic processes rather than a fundamental aspect of reality. His research suggests that the apparent flow of time results from statistical relationships between large numbers of particles rather than representing an objective feature of spacetime geometry. The extreme limit of time dilation at light speed creates the mathematical singularity that lies at the heart of our central paradox. For photons traveling at exactly light speed, the gamma factor becomes infinite, meaning infinite time dilation that stops time completely. This mathematical prediction implies that photons experience no passage of time during their journeys, regardless of the distances they traverse or the time intervals observed by other reference frames. Yet this infinite time dilation doesn't prevent photons from carrying information and energy across cosmic distances. Light from distant galaxies reaches our telescopes after traveling for billions of years from our perspective, yet from the photon's perspective, emission and absorption occur at the same instant with zero time elapsed. This apparent contradiction reveals deep truths about the nature of information transfer and causality in our universe. The resolution of this paradox requires understanding that photons exist at the boundary of spacetime geometry, where conventional concepts of reference frames and temporal flow break down, while we can mathematically describe what happens as massive objects approach light speed. Photons themselves cannot be said to have reference frames in the usual sense because they exist perpetually at the mathematical limit where standard relativistic relationships become singular. Dr. Leonard Susskind of Stanford University emphasizes that photons live on the light cone, the mathematical boundary in spacetime that separates causally connected regions from causally disconnected ones. This boundary existence gives light its unique properties, enabling it to connect any two points in spacetime instantaneously from its own perspective while still requiring finite time intervals when observed from other reference frames. Understanding time dilation provides essential groundwork for resolving the light-speed paradox, but the complete solution requires investigating how length contraction works in conjunction with time dilation and examining what these effects mean for the photon-s relationship to distance and spacetime geometry. Length contraction while time dilation describes how time slows down for objects moving at high velocities. Length contraction reveals the complementary effect where distances shrink in the direction of motion together. These phenomena create the photon's paradoxical relationship to distance from light's perspective. The vast expanses of space contract to zero length, eliminating any distance to traverse during its timeless journey. Length contraction, also known as Lorentz contraction after Hendrik Lorentz, who first derived the mathematical relationships, predicts that objects appear shortened in their direction of motion by exactly the same factor that governs time dilation. An object moving at velocity v relative to an observer will appear contracted in length by a factor of 1 divided by gamma, where gamma equals 1 divided by the square root of 1 minus v squared per c squared. This means that as an object approaches light speed, it becomes increasingly compressed in its direction of motion from the perspective of stationary observers. At 50% of light speed, lengths contract by about 13%. At 90% of light speed, objects shrink to about 44% of their rest length. At 99% of light speed, they compress to just 14% of their original size. At 99.9% of light speed, objects contract to merely 4.5% of their rest dimensions. The mathematical limit occurs at exactly light speed, where the contraction factor becomes infinite. This infinite length contraction means that from the perspective of an object moving at light speed, all distances in the direction of motion shrink to exactly zero. A photon traveling from the Andromeda Galaxy to Earth would experience the 2.5 million light-year distance as literally no distance at all, zero separation between source and destination. Professor John Wheeler of Princeton University, who coined the term black hole, described length contraction as revealing the dynamic, observer-dependent nature of spatial measurement. Space isn't the fixed, absolute arena that Newton imagined, but rather a flexible aspect of spacetime geometry that responds to motion in mathematically precise ways. What we measure as distance depends fundamentally on our state of motion relative to the objects being measured. The physical mechanism underlying length contraction emerges from the relativity of simultaneity, the fact that events simultaneous in one reference frame may be separated in time when observed from frames moving at different velocities. The length of an object is determined by simultaneously measuring the positions of its endpoints, but what counts as simultaneous depends on the observer's reference frame. When an object moves at high velocity, observers in different reference frames disagree about the simultaneity of measurements at the object's front and rear endpoints. This disagreement about simultaneity translates directly into disagreement about the object's measured length. The faster the object moves, the greater the disagreement about simultaneity becomes, leading to increasingly dramatic length contraction effects. Experimental verification of length contraction has proven challenging because it requires measuring the dimensions of objects moving at relativistic speeds, which is technically difficult. However, indirect confirmations have been obtained through various experimental approaches that demonstrate the reality of spatial contraction effects predicted by special relativity. One confirmation comes from studies of cosmic ray particles moving at velocities close to light speed. These particles interact with matter in ways that depend on their effective cross-sectional areas, which are altered by length contraction effects. Measurements of interaction rates confirm that high-velocity particles behave as if they possess the contracted dimensions predicted by special relativity. Particle accelerator experiments provide additional evidence through the behavior of particle beams at relativistic velocities. The focusing and defocusing of high-energy particle beams depends on their transverse dimensions, which are affected by length contraction in the direction of motion. Accelerator designers must account for these relativistic effects to achieve proper beam control and targeting. The Michelson-Morley experiment, performed in 1887, inadvertently provided early evidence for length contraction effects. This experiment attempted to measure Earth's motion through the hypothetical luminiferous ether by comparing light travel times in different directions. The null result of this experiment can be explained by length contraction of the experimental apparatus in the direction of Earth's motion through space. Modern experiments using atomic clocks and laser interferometry have provided increasingly precise confirmations of length contraction effects. The relationship between length contraction and time dilation isn't coincidental but reflects the underlying unity of space and time in four-dimensional spacetime. The Lorentz transformation equations show that space and time coordinates are mixed together when changing between reference frames, with spatial separations in one frame becoming temporal separations in another frame and vice versa. This spacetime mixing explains why length contraction and time dilation involve exactly the same mathematical factor. They represent different aspects of the same underlying geometric transformation in four-dimensional spacetime. Motion through space necessarily involves rotation in spacetime. Mixing spatial and temporal coordinates according to the mathematics of hyperbolic geometry. Dr. Hermann Minkowski, Einstein's former mathematics professor, developed the geometric interpretation of special relativity that reveals length contraction and time dilation as different projections of the same four-dimensional spacetime relationships. Minkowski spacetime diagrams show how spatial and temporal measurements depend on the orientation of the observer's reference frame in four-dimensional spacetime. The extreme case of length contraction at light speed creates a fundamental asymmetry in the photon-s relationship to spacetime. While massive objects experience finite length contraction and time dilation as they approach light speed, photons exist perpetually at the mathematical limit where these effects become infinite. From the photon's perspective, all spatial distances contract to zero while all temporal intervals dilate to infinity. This infinite length contraction resolves part of our central paradox by explaining how photons can traverse cosmic distances without experiencing any distance to travel. The 93 million miles between the Sun and Earth contracts to zero length from the photon's perspective, eliminating any spatial separation that would need to be crossed during the 8-minute journey up, served from Earth's reference frame. Yet this raises deeper questions about the nature of spatial separation and distance measurement. If photons experience zero distance between any two points they connect, what maintains the spatial structure of the universe? How can electromagnetic radiation carry information about spatial relationships when space itself contracts to zero from light's perspective? The answer lies in understanding that length contraction affects only the spatial dimensions parallel to the direction of motion. Distances perpendicular to motion remain unchanged, preserving the geometric relationships necessary for information transfer and causal structure. A photon traveling from a distant star to Earth experiences zero distance in its direction of travel but maintains normal spatial relationships in the transverse directions. Professor Sean Carroll of Caltech emphasizes that length contraction and time dilation work together to preserve causal relationships and information content while enabling instantaneous connection across arbitrary distances from the photon's perspective. This preservation of causality while achieving instantaneous connection represents one of the most elegant features of relativistic spacetime geometry. The mathematical singularities that occur at light speed, infinite time dilation, and infinite length contraction reveal that photons exist at a special boundary in spacetime, where conventional concepts of reference frames break down. While we can mathematically analyze what happens as massive objects approach light speed, photons themselves cannot be said to have reference frames in the usual sense because they exist perpetually at the singular boundary. This boundary existence has profound implications for understanding electromagnetic radiation and information transfer. Photons serve as the mediators that enable causal connections across spacetime while themselves existing outside the normal framework of temporal flow and spatial separation. They connect events that are space-like, separated events that cannot be connected by any massive object traveling slower than light speed. Understanding length contraction provides crucial insight into how photons relate to distance. But resolving the complete paradox requires investigating the deeper nature of spacetime geometry and examining what it means for massless particles to exist at the boundary of causal structure. The infinite length contraction experienced by photons eliminates distance from their perspective, while preserving the spatial relationships that make electromagnetic information transfer possible. Spacetime geometry, the resolution of light's paradoxical relationship to time and distance, requires understanding the deeper geometric structure of spacetime itself, the four-dimensional continuum that unifies space and time into a single mathematical framework. Einstein's general relativity reveals that spacetime isn't merely a passive stage where physical events occur, but an active participant that curves and bends in response to matter and energy, creating the phenomena we interpret as gravitational effects and influencing how light propagates through the universe. The geometric approach to spacetime was pioneered by Hermann Minkowski, who recognized that special relativity could be understood as geometry in four-dimensional space where time serves as the fourth coordinate. Minkowski spacetime diagrams represent events as points in a four-dimensional continuum where spatial coordinates x, y, and z are supplemented by a time coordinate ct, with c representing the speed of light to ensure dimensional consistency. In this geometric framework, the motion of objects through spacetime traces out curves called world lines. Massive objects that remain at rest in space follow world lines that extend only through the time dimension, appearing as vertical lines in spacetime diagrams. Objects moving through space follow tilted world lines that extend through both spatial and temporal dimensions, with the tilt angle corresponding to their velocity through space. Light rays follow special world lines called null geodesics that represent motion at exactly the speed of light through spacetime. These null geodesics have a unique geometric property. They lie along the light cone, a double cone structure that emanates from every event in spacetime and defines the boundary between regions that can be causally connected to that event and regions that cannot. The light cone structure reveals why the speed of light represents a fundamental limit in nature. Events inside an object's past light cone could have influenced that object, while events inside its future light cone can potentially be influenced by that object. Events outside the light cone cannot have any causal relationship with the object because no signal traveling at or below light speed could connect them. This geometric understanding illuminates the photon's unique relationship to spacetime, while massive objects follow time-like world lines that have finite slopes in spacetime diagrams. Photons follow null world lines that lie exactly on the light cone surface. This boundary position gives light its special properties. It can connect any two events in spacetime that lie on each other as light cones, regardless of their spatial separation. Professor Kip Thorne of Caltech emphasizes that null geodesics have the remarkable property that their spacetime interval equals zero. The spacetime interval, represented by ds, is the relativistic generalization of distance that accounts for both spatial and temporal separations. For massive objects, this interval is positive for time-like separations and negative for space-like separations, but for null geodesics followed by light, the interval equals exactly zero. This zero spacetime interval provides the mathematical foundation for understanding the photons' perspective from the viewpoint of spacetime geometry. Events connected by null geodesics have zero separation in the four-dimensional spacetime metric. The photon's emission and absorption occur at points that are separated by zero distance in the curved geometry of spacetime. Despite being separated by vast spatial distances and time intervals when measured in any particular reference frame, the mathematical expression for the spacetime interval in special relativity takes the form ds equals c squared dt squared plus dx squared plus d squared plus dz, where dt represents the time interval and dx, d represent spatial intervals between two events. For photons traveling at speed c, the spatial distance traveled equals c times the time interval, so dx plus d squared plus dz equals c dt, making the spacetime interval equal to zero. This zero interval remains invariant across all reference frames. All observers agree that photons follow null geodesics with zero spacetime intervals, regardless of their own motion or the photon's apparent frequency and wavelength in their frame. This invariance of the null condition ensures that the speed of light remains constant for all observers, as required by the fundamental postulates of special relativity. The geometry of spacetime also explains how information can be transferred instantaneously from the photon's perspective while still requiring finite time intervals from other reference frames. Information carried by electromagnetic radiation doesn't travel through space in the conventional sense but rather connects events that lie on each other as light cones. With zero spacetime separation. Dr. Carlo Rovelli of Aix-Marseille University describes this as revealing that causality operates through the geometric structure of spacetime rather than through temporal sequence in any particular reference frame. Events can be causally connected if they can be linked by null or time-like geodesics, regardless of whether they appear simultaneous or sequential to any particular observer. This geometric understanding resolves the apparent paradox of how light can traverse vast distances while experiencing no time or distance. From the spacetime geometry perspective, photons don't travel through space and time, but rather exist as geometric connections between events that have zero spacetime separation. The photon itself doesn't experience duration or distance because it exists as a null geodesic, a geometric feature of spacetime rather than an object moving through spacetime. The curvature of spacetime in general relativity adds additional complexity to this geometric picture. In the presence of massive objects, spacetime curves and the geometry of null geodesics becomes more complex. Light follows curved paths through curved spacetime, leading to phenomena like gravitational lensing, time delay of electromagnetic signals in gravitational fields, and the redshift of light climbing out of gravitational wells. These gravitational effects on light propagation provide experimental confirmations of the geometric nature of spacetime and the special relationship between electromagnetic radiation and spacetime structure. The bending of starlight during solar eclipses, first observed by Arthur Eddington in 1919, confirmed Einstein's prediction that light follows curved geodesics through curved spacetime. The geometric framework also illuminates why photons cannot be slowed down or sped up. They must always follow null geodesics at exactly the speed of light. Unlike massive objects, which can have various velocities and follow different time-like geodesics, photons are constrained to follow null geodesics exclusively. This constraint ensures that electromagnetic radiation always propagates at light speed in any local reference frame. Modern cosmology relies heavily on the geometric understanding of light propagation through spacetime. The cosmic microwave background radiation that fills the universe represents photons that have been traveling along null geodesics since the era of recombination, about 380,000 years after the Big Bang. From these photons' perspective, their emission and our current detection occur at the same instant with zero spacetime separation. The geometric approach to spacetime also provides insight into quantum field theory and the nature of virtual particles. In quantum electrodynamics, electromagnetic interactions occur through the exchange of virtual photons that can propagate along space-like geodesics, connecting events that cannot be linked by real photons. These virtual photons exist entirely within the mathematical framework of quantum field theory and do correspond to observable electromagnetic radiation. Understanding spacetime geometry as the foundation for light's unique properties reveals that the photon's paradoxical relationship to time and distance reflects fundamental features of the universe's mathematical structure rather than limitations of our understanding. Light exists at the boundary of spacetime geometry, where conventional concepts of motion, duration, and distance break down and are replaced by geometric relationships between events connected by null geodesics. This geometric perspective provides the foundation for understanding how electromagnetic radiation can simultaneously connect distant regions of spacetime instantaneously from its own perspective, while enabling the transmission of information and energy across cosmic distances observed from other reference frames. Photon perspectives. Understanding what it means for a photon to experience its journey requires grappling with one of the most profound conceptual challenges in modern physics. While we can mathematically describe what happens to space and time from the perspective of objects approaching light speed, photons themselves exist at the mathematical singularity where conventional concepts of reference frames, experience, and perspective break down completely. The question of the photon's perspective immediately confronts us with fundamental limitations in our ability to apply familiar concepts to massless particles. Massive objects can have reference frames, coordinate systems in which they remain at rest, but photons cannot be at rest in any reference frame because they always move at the speed of light. This means we cannot literally ask what a photon sees or experiences during its journey because these concepts presuppose the existence of a reference frame that doesn't exist for light. Yet the mathematical framework of special relativity allows us to approach this question by examining the limiting behavior as massive objects approach light speed. As an object's velocity increases towards c, time dilation causes its clocks to run slower and slower until, in the limit, time stops completely. Simultaneously, length contraction causes distances to shrink until, at light speed, all distances in the direction of motion contract to zero. Professor Brian Greene of Columbia University explains this limiting behavior through the metaphor of spacetime navigation. All objects move through four-dimensional spacetime at a constant total velocity equal to the speed of light. Objects at rest move entirely through the time dimension, experiencing maximum time flow and zero spatial motion. As objects begin moving through space, they must divert some of their motion from time into spatial dimensions, causing time to slow down. At light speed, all motion occurs through spatial dimensions with none remaining for motion through time. This explains why photons experience no passage of time. They use all their spacetime velocity for motion through space, leaving none for motion through time. From this perspective, photons exist in a state of eternal present, where emission and absorption occur at the same instant regardless of the spatial and temporal separations observed by other reference frames. The mathematical description of the photon's perspective involves taking the limit as velocity approaches c in the Lorentz transformation equations. In this limit, the time coordinate dt approaches zero while the spatial coordinates dx contract to zero in the direction of motion. This double limiting behavior means that photons experience both zero time elapsed and zero distance traveled, regardless of the spacetime separation between emission and absorption events. Dr. Sean Carroll of Caltech emphasizes that this mathematical limiting behavior reveals photons as existing on the boundary of spacetime geometry. While massive objects exist within spacetime and move along time like worldlines, photons exist on the light cone boundary where the normal concepts of interior and exterior to spacetime break down. They neither exist inside spacetime nor outside it, but rather define the geometric boundary that separates causally connected regions from causally disconnected ones. This boundary existence gives photons their unique causal properties. While massive objects can influence only events in their future light cone and can be influenced only by events in their past light cone, photons themselves constitute the light cone structure that defines these causal relationships. They serve as the geometric framework that enables causal connections across spacetime while themselves existing outside the normal temporal relationships that govern massive matter. The question of photon experience becomes even more complex when we consider quantum mechanical properties. Classical relativity treats photons as point particles following well-defined trajectories through spacetime. But quantum mechanics reveals electromagnetic radiation as exhibiting both particle and wave properties. The wave nature of light suggests that photons don't follow single definite paths, but rather exist as probability amplitudes distributed across all possible paths connecting emission and absorption points. Quantum field theory provides additional insight into the photon's relationship to spacetime. In this framework, photons emerge as excitations of the electromagnetic field, a mathematical entity that permeates all of spacetime. Rather than being objects that move through space and time, photons represent disturbances in the field structure that propagate according to the wave equation for electromagnetic radiation. This field perspective suggests that asking about the photon's subjective experience may be asking the wrong question. Instead of imagining photons as tiny objects with internal experiences, we might better understand them as geometric features of spacetime that connect events instantaneously from their own perspective while enabling information transfer across finite spacetime intervals from other reference frames. The concept of photon perspective becomes particularly intriguing when considering cosmological distances. Light from the cosmic microwave background has been traveling for approximately 13.8 billion years from our perspective, crossing the entire observable universe. Yet from the photons' perspective, their emission from the surface of last scattering and their absorption by our radio telescopes occur at exactly the same instant with zero time elapsed and zero distance traversed. This cosmological example reveals the profound implications of the photon perspective for our understanding of cosmic connectivity. Every photon that has ever reached Earth from nearby stars, distant galaxies, or the cosmic microwave background experienced zero time during its journey. This means that from the perspective of electromagnetic radiation, the entire observable universe is instantaneously connected, with all electromagnetic events occurring simultaneously in the photon reference frame. Dr. Michio Kaku of City College of New York describes this as revealing a hidden unity underlying the apparent separation of cosmic events. While we observe stars and galaxies separated by vast distances and time intervals, the electromagnetic radiation that connects us to these distant objects experiences no separation whatsoever. Light serves as an instantaneous communication medium from its own perspective, connecting all electromagnetic events across cosmic space and time. The photon perspective also illuminates fundamental questions about information transfer and causality. Information carried by electromagnetic radiation doesn't travel through space in the conventional sense, but rather connects events that have zero space-time separation from the photon's viewpoint. This instantaneous connection enables rapid information transfer while preserving causal relationships and preventing paradoxes that would arise from faster-than-light communication. Modern physics extends the concept of photon perspective through virtual particle interactions. Described by quantum electrodynamics, virtual photons that mediate electromagnetic forces between charged particles can propagate along space like geodesics, connecting events that are space-like separated. These virtual photons exist entirely within the mathematical framework of quantum field theory and don't correspond to observable electromagnetic radiation. Yet they play crucial roles in electromagnetic interactions. The limiting behavior that defines the photon perspective also appears in other physical contexts involving massless particles. Gravitons, the hypothetical quanta of gravitational radiation, would experience the same zero-time and zero-distance relationships as photons. Any massless particle must travel at light speed and would exhibit the same boundary relationship to spacetime geometry that characterizes electromagnetic radiation. Understanding the photon perspective requires abandoning anthropocentric concepts of experience and embracing the mathematical relationships that govern massless particles. At the boundary of spacetime geometry, photons don't experience their journeys in any meaningful sense, but rather exist as geometric connections between events that define the causal structure of spacetime itself. This geometric interpretation resolves the apparent paradox of how light can traverse cosmic distances while experiencing no time or distance. From the photon perspective, there is no journey to experience because emission and absorption occur at points with zero spacetime separation. The photon exists as an instantaneous geometric link that enables information transfer across arbitrary spatial and temporal intervals, while itself remaining outside the normal framework of motion through spacetime. Quantum mechanics. The intersection of quantum mechanics with special relativity reveals additional layers of complexity in understanding how light relates to time and distance. While classical relativity treats photons as point particles following definite trajectories through spacetime, quantum mechanics describes electromagnetic radiation as exhibiting fundamental wave-particle duality and existing as probability amplitudes distributed across all possible paths between emission and absorption events. The quantum mechanical description of photons emerges from the quantization of electromagnetic fields described by Maxwell's equations, rather than being discrete particles in the classical sense. Photons represent excitations of the electromagnetic field, a quanta of electromagnetic energy that propagate according to the wave equation while exhibiting particle-like properties when detected. This dual nature profoundly affects how we understand the photon's relationship to spacetime. In quantum electrodynamics, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, Electromagnetic interactions occur through the exchange of virtual photons between charged particles. These virtual photons differ fundamentally from the real photons we observe as light. They can have any energy and momentum relationship, including configurations that would violate the normal relativistic energy-momentum relation for real particles. Virtual photons can propagate along space-like geodesics, connecting events that are separated by space-like intervals and cannot be connected by any signal traveling at or below light speed. This space-like propagation enables instantaneous electromagnetic interactions between charged particles, explaining how electromagnetic forces operate without apparent time delays despite the finite speed of light. Dr. Richard Feynman's path integral formulation of quantum mechanics provides profound insight into how photons propagate through spacetime. According to this approach, a photon doesn't follow a single definite path from emission to absorption, but rather explores all possible paths simultaneously, with each path contributing a complex probability amplitude to the overall quantum mechanical description of the interaction. The sum over all possible paths includes not only the classical straight-line trajectory that light appears to follow, but also elaborate curved paths that loop through spacetime, travel backward in time, and violate classical conservation laws. These quantum mechanical paths interfere with each other according to complex phase relationships, with the interference patterns determining the probability of photon detection at various locations. This path integral perspective reveals that the photon's relationship to time and distance involves quantum mechanical superposition across all possible spacetime trajectories, while the classical trajectory that dominates the sum over paths corresponds to light traveling at speed c along null geodesics. Quantum mechanics includes contributions from paths that involve different relationships to time and distance. The uncertainty principle plays a crucial role in the quantum mechanical description of photon propagation. The energy-time uncertainty relation, delta E and delta T, is greater than or equal to I2, whereas the reduced Planck constant allows virtual particles to exist for brief periods with energies that would violate classical energy conservation. Virtual photons can have arbitrary energies and momenta as long as they exist for sufficiently short times consistent with the uncertainty principle. Professor Freeman Dyson of the Institute for Advanced Study emphasizes that virtual particle interactions reveal the quantum vacuum as a seething ocean of particle-antiparticle pairs and virtual gauge bosons that constantly appear and disappear on timescales too brief for direct observation. This quantum vacuum activity affects the propagation of real photons through modifications to the electromagnetic field that can be measured through extremely precise experiments. The Casimir effect provides experimental evidence for virtual photon interactions and the reality of quantum vacuum fluctuations. Two parallel metal plates placed very close together in vacuum experience an attractive force due to the restriction of virtual photon modes between the plates compared to the unrestricted virtual photon modes outside the plates. This measurable force demonstrates the physical reality of virtual electromagnetic field fluctuations. Quantum field theory reveals that the classical concept of electromagnetic radiation as waves propagating through empty space must be replaced by the more sophisticated picture of photons as excitations of a quantum field that permeates all of spacetime. The electromagnetic field itself possesses a rich quantum structure with zero-point energy fluctuations that persist even in the absence of any real photons. The quantum mechanical description of photons also illuminates their relationship to causality and information transfer. While virtual photons can propagate along space-like geodesics and enable instantaneous electromagnetic interactions, real photons that carry observable energy and information must propagate along null geodesics at exactly light speed, preserving causal relationships and preventing faster-than-light information transfer. Dr. Steven Weinberg of the University of Texas emphasizes that the quantum mechanical constraints on real photon propagation ensure that observable electromagnetic phenomena respect the causal structure of spacetime established by special relativity. Virtual particle interactions can violate energy momentum conservation temporarily, but real particle interactions that carry observable energy and information must satisfy relativistic constraints. The quantum mechanical treatment of photon polarization reveals additional complexity in electromagnetic radiation's relationship to spacetime. Polarization represents the orientation of the electric field vector as electromagnetic radiation propagates, and quantum mechanics describes polarization as a two-dimensional quantum mechanical system with superposition states and entanglement properties. Quantum entanglement between photons creates correlations that appear to violate classical concepts of locality and separation. Entangled photons can exhibit correlated properties regardless of their spatial separation, leading to phenomena that Einstein famously criticized as spooky action at a distance. These quantum correlations respect the constraints of special relativity by not enabling faster-than-light information transfer. But they reveal non-local quantum mechanical relationships that transcend classical spacetime separations. Recent experiments in quantum optics have demonstrated entanglement between photons separated by hundreds of kilometers, confirming that quantum mechanical correlations can persist across macroscopic distances without violating relativistic causality constraints. These experiments reveal that quantum mechanics introduces non-local correlations that complement the local causal relationships established by classical relativity. The quantum mechanical description of photon creation and annihilation processes provides insight into how electromagnetic radiation interacts with matter at the most fundamental level. When atoms emit or absorb photons, the process occurs instantaneously from the perspective of the electromagnetic field. But the quantum mechanical probability amplitudes for these processes depend on the detailed spacetime geometry of the interaction region. Quantum electrodynamics predicts subtle corrections to electromagnetic interactions that arise from virtual particle loops and quantum vacuum fluctuations. These quantum corrections affect the propagation of real photons through modifications to their interaction with charged particles, leading to measurable effects like the anomalous magnetic moment of the electron and the Lamb shift in atomic energy levels. The integration of quantum mechanics with special relativity through quantum field theory reveals that photons exist as quantum mechanical excitations of a relativistic field that respects the geometric structure of spacetime while exhibiting fundamentally quantum mechanical properties. This quantum field theoretical perspective provides the most complete description of how electromagnetic radiation relates to time, distance, and causality. The quantum mechanical treatment of electromagnetic radiation resolves some aspects of the photon's paradoxical relationship to time and distance, while introducing additional quantum mechanical mysteries. While photons still experience zero time and zero distance in their propagation from emission to absorption, quantum mechanics reveals this as occurring through superposition of probability amplitudes across all possible spacetime paths rather than through motion along a single classical trajectory. Understanding the quantum mechanical aspects of photon propagation provides essential insight into the fundamental nature of electromagnetic radiation and its relationship to spacetime geometry. But the complete resolution of light's paradoxical properties requires examining how these quantum mechanical effects integrate with relativistic geometry and causality constraints. Massless particles. The unique relationship between photons and spacetime geometry stems from their fundamental property as massless particles, which constrains them to travel at exactly the speed of light and exist perpetually at the boundary of spacetime structure. Understanding why massless particles must behave this way reveals deep connections between mass, energy, momentum, and the geometric structure of spacetime that govern all electromagnetic phenomena. The relationship between mass, energy, and momentum in special relativity is described by the relativistic energy-momentum equation, E squared equals pc squared plus mc squared squared, where E represents total energy, P represents momentum, M represents rest mass, and C represents the speed of light. For massive particles, the rest mass term mc contributes to the total energy even when the particle is at rest. But for massless particles, this term vanishes completely. When m equals 0, the energy-momentum equation simplifies to E equals pc, meaning that the total energy of a massless particle equals the magnitude of its momentum multiplied by the speed of light. This relationship constrains massless particles to move at exactly light speed because any other velocity would violate the fundamental relationship between energy and momentum established by special relativity. Professor Steven Weinberg of the University of Texas explains that this constraint emerges from the requirement that energy and momentum transform consistently under Lorentz transformations. Between different reference frames, the energy-momentum force vector must have the same magnitude in all reference frames, which is only possible for massless particles if they travel at exactly light speed in every frame. The absence of rest mass eliminates the possibility of bringing a photon to rest or changing its speed through interactions with other particles. While massive particles can be accelerated or decelerated by exchanging energy and momentum with other systems, massless particles must maintain constant speed c in all circumstances. They can change direction through scattering interactions, and their energy and momentum can be modified through frequency shifts, but their speed remains invariant. This invariant speed property gives photons their unique role in establishing the causal structure of spacetime. The speed of light represents the maximum speed at which information and causal influences can propagate through spacetime, and massless particles naturally propagate at this maximum speed. They serve as the carriers of electromagnetic interactions and define the light cone structure that separates causally connected regions of spacetime from causally disconnected ones. The massless nature of photons also explains their infinite range and the inverse square law behavior of electromagnetic forces, and like massive gauge bosons that mediate short-range interactions. Massless photons can propagate across arbitrary distances without attenuation, enabling electromagnetic forces and radiation to operate across cosmic scales. This infinite range property makes electromagnetism one of the dominant forces shaping large-scale cosmic structure. Dr. Maury Gell-Mann of Caltech, who developed much of the modern theory of elementary particles, emphasized that the massless property of photons represents a fundamental symmetry of nature, the Gauge asymmetry of electromagnetic theory. This symmetry requires that the electromagnetic field remain invariant under certain mathematical transformations, and this invariance can only be preserved if the photon remains exactly massless. Any mechanism that gave photons a small mass would break electromagnetic gauge symmetry and fundamentally alter the structure of electromagnetic theory. Experiments have placed extremely stringent upper limits on any possible photon mass, with current bounds indicating that if photons have any mass at all, it must be less than 10 to 18 times the electron mass, essentially confirming the theoretical prediction of exact masslessness. The massless property of photons connects to deep questions in particle physics about the origin of mass in general, the Higgs mechanism, which explains how fundamental particles acquire mass through interactions with the Higgs field, specifically excludes photons from this mass generation process. Photons remain massless because they don't couple to the Higgs field, preserving electromagnetic gauge symmetry. Other particles that are predicted to be massless include gravitons, the hypothetical quanta of gravitational radiation, and gluons, which mediate the strong nuclear force. Gravitons must be massless to ensure that gravity has infinite range like electromagnetism, while gluons are massless due to the gauge symmetry of quantum chromodynamics, though they are confined within hadrons and cannot propagate freely through space. The massless nature of photons also determines their quantum mechanical properties and statistical behavior. Photons are bosons with integer spin, specifically spin 1 particles, which means they obey Bose-Einstein statistics rather than Fermi-Dirac statistics. This statistical behavior allows multiple photons to occupy the same quantum state, enabling phenomena like laser operation and the coherent electromagnetic radiation produced by astronomical sources, and light massive particles, which have 3 degrees of freedom corresponding to 3 possible spin orientations relative to their direction of motion. Massless particles with spin 1 have only 2 physical polarization states. This reduction from 3 to 2 polarization states reflects the absence of a rest frame for massless particles. There's no reference frame in which the particle is at rest, and its spin can be measured relative to an arbitrary spatial direction. Professor Gerard T. Hooft of Utrecht University notes that the massless property of gauge bosons like photons plays a crucial role in renormalization procedures that eliminate infinite quantities. From quantum field theory calculations, the specific mathematical structure of massless gauge theories enables the cancellation of divergences that would otherwise make electromagnetic theory mathematically inconsistent. The propagation of massless particles through curved spacetime and general relativity exhibits unique properties that differ from the behavior of massive matter. Massless particles follow null geodesics, the straightest possible paths through curved spacetime, while massive particles follow time-like geodesics. This geometric difference explains why light, rays, and particle trajectories can differ in strong gravitational fields. Gravitational effects on massless particles manifest through frequency shifts rather than changes in speed. When photons climb out of gravitational wells, they experience redshift. Their frequency decreases and wavelength increases, but their speed remains exactly c in any local reference frame. This gravitational redshift provides one of the fundamental tests of general relativity and has been confirmed through numerous experiments. The massless nature of photons enables them to carry information about the spacetime geometry through which they propagate, gravitational lensing effects, where light rays are bent by massive objects, provide direct observational evidence for spacetime curvature, and have become powerful tools for studying dark matter, dark energy, and cosmic structure formation. Recent theoretical developments in string theory and quantum gravity suggest that the massless property of photons may be connected to deeper principles governing the structure of spacetime. At the Planck scale, some theories predict that Lorentz symmetry, which ensures the massless property of photons, may be slightly violated at extremely high energies, leading to tiny modifications in electromagnetic propagation that could be detectable through precision astronomical observations. The study of high-energy cosmic ray photons and gamma rays from distant astronomical sources provides sensitive tests of photon masslessness and Lorentz symmetry. Any violations would manifest as energy-dependent variations in the speed of light or time delays between photons of different energies from the same source. But current observations confirm Lorentz symmetry and photon masslessness to extraordinary precision. Understanding massless particles reveals that photons occupy a unique position in the structure of fundamental physics. They exist at the boundary between matter and spacetime geometry, serving as the mediators of electromagnetic interactions while defining the causal structure that governs all physical processes. Their massless property ensures that they propagate at the maximum possible speed and experience the infinite time dilation and length contraction that eliminate time and distance from their perspective. This massless property provides the foundation for understanding how electromagnetic radiation can connect distant regions of spacetime instantaneously from its own perspective, while preserving causal relationships and enabling information transfer across finite spacetime intervals from other reference frames. Information transfer: the apparent paradox of how light can carry information across vast distances while experiencing zero time and zero distance from its own perspective, reveals fundamental principles about the nature of information, causality, and communication in our universe. Understanding how electromagnetic radiation transfers information without violating relativistic constraints provides crucial insight into the structure of physical law and the mechanisms that enable complex systems to process and exchange information. Information theory, developed by Claude Shannon in the 1940s, defines information as the reduction of uncertainty about a system state. When electromagnetic radiation carries information from a distant source to a detector, it reduces uncertainty about the conditions at the source by encoding those conditions in the properties of the electromagnetic field, its frequency, amplitude, phase, and polarization state. From the perspective of information theory, the physical mechanism of information transfer matters less than the mathematical relationships between the source state, the transmission channel, and the receiver state. Electromagnetic radiation serves as an extremely efficient information channel because it can encode information in multiple independent variables while propagating at the maximum possible speed through spacetime. Dr. John Wheeler of Princeton University, who coined the phrase "it from bit," argued that information represents the fundamental constituent of reality, with matter and energy emerging as secondary manifestations of more basic informational relationships. From this perspective, photons don't carry information so much as they constitute information. They are informational relationships between events in spacetime. The quantum mechanical description of electromagnetic radiation reveals that information encoding occurs through the quantum states of photons rather than through classical wave properties. A single photon can carry information through its polarization state, which represents a quantum mechanical two-level system capable of storing one bit of quantum information. Multiple photons can carry larger amounts of information through quantum entanglement and superposition states. Quantum information theory demonstrates that electromagnetic radiation can carry more information per photon than classical physics predicts through quantum mechanical properties like superposition and entanglement. Quantum communication protocols can achieve information transfer rates that exceed classical limits while maintaining security through the fundamental properties of quantum measurement. The speed of information transfer through electromagnetic radiation respects the relativistic constraint that information cannot propagate faster than light speed, preserving causal relationships and preventing paradoxes that would arise from faster than light communication. While photons experience zero time during their propagation, information transfer still requires finite time intervals when measured from reference frames of sources and receivers. Professor Anton Zeilinger of the University of Vienna, a pioneer in quantum communication, emphasizes that quantum entanglement between photons can create correlations that appear to involve instantaneous information transfer across arbitrary distances. However, careful analysis reveals that these quantum correlations cannot be used to transmit usable information faster than light speed, preserving relativistic causality while enabling new forms of quantum communication. The relationship between information transfer and spacetime geometry becomes particularly intriguing when considering cosmological distances. Light from distant galaxies carries information about conditions billions of years in the past, enabling astronomers to study the history and evolution of the universe from the photons' perspective. They connect past cosmic events directly to present observations with zero spacetime separation. This cosmological information transfer reveals that electromagnetic radiation serves as a mechanism for preserving and transmitting information across cosmic time scales. The cosmic microwave background radiation carries information about conditions approximately 380 years after the Big Bang, when the universe first became transparent to electromagnetic radiation. This information has been preserved in the photon states for nearly 14 billion years of cosmic evolution. Modern fiber optic communication systems demonstrate practical applications of electromagnetic information transfer that exploit the unique properties of light propagation. Information is encoded in laser pulses that propagate through optical fibers at nearly light speed, enabling global communication networks that transfer enormous quantities of information with minimal time delays. The efficiency of optical communication stems from the coherence properties of laser light and the low attenuation of electromagnetic radiation in optical fibers. Single-mode optical fibers can transmit information over hundreds of kilometers with minimal signal degradation, while wavelength division multiplexing allows multiple independent information channels to share the same fiber through different optical frequencies. Quantum cryptography protocols exploit the quantum mechanical properties of photons to achieve theoretically unbreakable security for information transmission. These protocols rely on the fundamental property that quantum measurements disturb quantum systems, making it impossible for eavesdroppers to intercept quantum-encoded information without detection. The security comes from quantum mechanics itself rather than computational complexity. The study of information transfer in black hole physics has revealed deep connections between thermodynamics, quantum mechanics, and spacetime geometry. Stephen Hawking's discovery that black holes emit thermal radiation suggests that information falling into black holes may not be permanently lost but rather encoded in the quantum states of the Hawking radiation that escapes to infinity. The black hole information paradox arises because quantum mechanics requires information conservation while general relativity suggests that information falling into black holes disappears permanently when the black holes evaporate through Hawking radiation. Resolving this paradox may require fundamental advances in our understanding of how information relates to spacetime geometry. At the quantum level, recent developments in holographic theories suggest that information about the interior of regions of spacetime may be completely encoded on their boundaries, with the interior serving merely as a computational convenience rather than fundamental physical reality. These holographic principles may explain how electromagnetic radiation can carry complete information about distant sources while propagating along null geodesics that experience zero spacetime intervals. Dr. Leonard Susskind of Stanford University argues that the holographic principle reveals information as more fundamental than spacetime geometry itself. From this perspective, electromagnetic radiation doesn't transfer information through spacetime but rather constitutes the informational relationships that give rise to our perception of spatial and temporal separation. Quantum error correction codes, developed for quantum computing applications, provide insight into how information can be preserved and transmitted reliably through noisy channels. These codes reveal that information possesses an abstract existence that can be maintained even when the physical systems that encode it are subject to decoherence and environmental interference. The application of quantum error correction to cosmology suggests that the universe itself may employ error correction mechanisms to preserve information across cosmic time scales. The apparent stability of physical laws and the persistence of complex structures over billions of years may result from quantum error correction processes operating at cosmological scales. Information transfer through electromagnetic radiation also enables the existence of complex biological and technological systems that depend on reliable communication across various distance and time scales, from the molecular processes that transfer genetic information to the neural networks that process sensory information. Electromagnetic interactions provide the physical basis for information processing in living systems. The study of biological photosynthesis reveals how living organisms exploit quantum mechanical properties of light to transfer energy and information with remarkable efficiency. Quantum coherence in photosynthetic complexes enables energy transfer that approaches theoretical limits while maintaining robustness against environmental decoherence. Recent research in quantum biology suggests that many biological processes exploit quantum mechanical phenomena to achieve performance that exceeds classical limits. Bird navigation, enzyme catalysis, and neural information processing may all involve quantum mechanical effects that enable biological systems to process information more efficiently than classical physics would permit. Understanding information transfer through electromagnetic radiation reveals that the photon's paradoxical relationship to time and distance enables rather than prevents reliable information transmission. The zero spacetime interval experienced by photons ensures that electromagnetic information transfer occurs without degradation due to temporal evolution, while the finite time intervals observed from other reference frames enable causal relationships and temporal sequencing necessary for complex information processing systems. Causality paradox. The paradox of causality in light propagation emerges from the apparent contradiction between the photon's timeless perspective and the obvious fact that electromagnetic phenomena exhibit clear temporal sequences when observed from any material reference frame. If photons experience zero time during their propagation, how can we reconcile this with the observation that electromagnetic events occur in definite temporal order and respect causal relationships that require finite time intervals? Classical causality requires that causes precede their effects in time, with sufficient interval between cause and effect to allow for the propagation of causal influences at finite speeds. This temporal sequence ensures logical consistency and prevents paradoxes where effects could influence their own causes. Yet from the photon's perspective, where time doesn't flow, the concepts of before and after become meaningless, apparently eliminating the temporal structure necessary for causal relationships. Professor John Stuart Bell of CERN, famous for Bell's theorem in quantum mechanics, argued that causality in relativistic physics must be understood through the light cone structure of spacetime rave, rather than through temporal sequence in any particular reference frame. Events can be causally related if they can be connected by signals traveling at or below light speed, regardless of their temporal ordering in specific coordinate systems. This light cone causality resolves the apparent paradox by recognizing that causal relationships are fundamentally geometric rather than temporal. Two events can be causally connected if they lie on each other's light cones if a signal traveling at light speed can connect them through spacetime. The photon's zero-time experience doesn't eliminate causality but rather reveals causality as operating through spacetime geometry rather than temporal sequence. The mathematical framework of special relativity makes this geometric causality precise through the concept of spacetime intervals. Events separated by time-like intervals, negative spacetime interval, can be causally connected by massive objects traveling slower than light. Events separated by null intervals, zero spacetime interval, can be causally connected by electromagnetic radiation traveling at light speed. Events separated by space-like intervals, positive spacetime interval, cannot be causally connected by any physical signal. From this geometric perspective, photons don't violate causality despite their timeless experience. They define the boundary of causal structure in spacetime. Electromagnetic radiation establishes the fastest possible causal connections between events, enabling information transfer at the maximum speed permitted by the structure of spacetime while respecting the geometric constraints that maintain logical consistency. Dr. Roger Penrose of Oxford University emphasizes that the light cone structure created by electromagnetic propagation provides the foundation for all causal relationships in spacetime, without the ability of light to connect distant events instantaneously from its own perspective, while requiring finite time from other perspectives. The universe would lack the causal coherence necessary for the existence of stable structures and predictable physical laws. The quantum mechanical treatment of causality introduces additional complexity through the phenomenon of quantum entanglement, where spatially separated particles can exhibit correlated properties that appear to violate locality constraints. Einstein famously criticized quantum entanglement as spooky action at a distance, arguing that it seemed to enable instantaneous influences across arbitrary spatial separations. However, detailed analysis of quantum entanglement reveals that it doesn't violate relativistic causality because entangled correlations cannot be used to transmit information faster than light speed, while measurement of one entangled particle instantly determines the state of its partner, regardless of separation. This correlation cannot be exploited for faster than light communication because the measurement results appear random until compared with measurements on the partner particle. Modern experiments with entangled photons have confirmed that quantum correlations can persist across hundreds of kilometers while respecting relativistic causality constraints. These experiments demonstrate that nature can exhibit non-local quantum correlations that transcend classical spacetime separations without enabling faster-than-light information transfer that would violate causal ordering. The study of causal paradoxes in general relativity reveals additional complexity when spacetime geometry becomes curved and the presence of massive objects. Light rays follow curved paths through curved spacetime, and in extreme cases, closed time-like curves can appear that would allow signals to travel into their own past, potentially creating grandfather paradox-type causality violations. These exotic spacetime geometries, including traversable wormholes and Alcubierre warp drives, appear to permit faster-than-light travel and communication that would violate causality. However, detailed analysis typically reveals that these solutions require exotic matter with negative energy density that may not exist in nature, or they develop instabilities that prevent their practical implementation. Stephen Hawking proposed the chronology protection conjecture, which suggests that the laws of physics somehow prevent the formation of closed time-like curves that would enable causality violations. According to this conjecture, quantum effects or other physical mechanisms intervene to maintain causal consistency whenever spacetime geometries threaten to permit time travel paradoxes. The relationship between electromagnetic propagation and causality becomes particularly intriguing when considering virtual particle interactions in quantum field theory. Virtual photons that mediate electromagnetic forces can propagate along space like geodesics, connecting events that are space-like separated and cannot be connected by any signal traveling at or below light speed. These virtual photon exchanges appear to violate causality by enabling instantaneous interactions between charged particles regardless of their spatial separation. However, virtual particles exist entirely within the mathematical framework of quantum field theory and cannot be observed directly. The observable effects of electromagnetic interactions always respect causality constraints and cannot be used to transmit information faster than light speed. Dr. Stephen Hawking's work on black hole thermodynamics revealed deep connections between causality, information theory, and the fundamental structure of spacetime. The event horizon of a black hole represents a causal boundary. Events inside the horizon cannot causally influence events outside, regardless of the time available for signal propagation. The information paradox in black hole physics arises from apparent conflicts between causality constraints and information conservation in quantum mechanics. If information falling into black holes is preserved in Hawking radiation, it must somehow escape from regions that are causally disconnected from the external universe, challenging our understanding of causal relationships in quantum gravity. Recent developments in holographic theories and ADS-CFT correspondence suggest that causality constraints may be more subtle than previously understood. These theories propose that information about the interior of regions of spacetime may be encoded on their boundaries in ways that respect causality while enabling information preservation that appears to violate local causal relationships. The study of quantum field theory in curved spacetime reveals that particle creation and annihilation processes in time-varying gravitational fields can exhibit apparent acausality. For example, the Hawking radiation emitted by black holes originates from vacuum fluctuations near the event horizon, where virtual particle pairs are separated by the gravitational field with one member falling into the black hole and the other escaping to infinity. This process appears to violate causality because the escaping particles carry energy away from the black hole without any apparent causal connection to the infalling matter that formed the black hole. However, detailed analysis reveals that the causal relationships are preserved through subtle correlations between the infalling matter and the outgoing Hawking radiation. Understanding causality in the context of electromagnetic propagation requires recognizing that the photon's timeless perspective doesn't eliminate causal relationships, but rather reveals their geometric foundation in spacetime structure. Electromagnetic radiation provides the fastest possible causal connections between events while respecting the fundamental constraints that maintain logical consistency and prevent paradoxes. The resolution of the causality paradox illuminates deep principles about the nature of time, information, and physical law. While photons experience no temporal flow during their propagation, they enable the causal relationships that give rise to temporal ordering and physical predictability when observed from material reference frames. This duality between timeless electromagnetic propagation and temporal causal structure represents one of the most profound features of relativistic spacetime geometry.